Hello, everyone. I'm going to talk about just-in-time compiler, which is JIT for short. Maybe you must be now sleepy, kind of, because it's day 3 and kind of tired. But I have a solution for you, which is this repository called RubyJIT Challenge, which is a tutorial for writing a RubyJIT. The goal of this talk is to make you a RubyJIT author, and this makes you one of them. And maybe writing a JIT is a fun experience, so you may not be kind of falling sleepy. So let's please give it a try. So who am I? I'm Kokubun. I'm working at the JIT team in the Ruby infrastructure team, in the Ruby and Rails infrastructure team at Shopify. And I maintain JIT at work and other projects like RJIT, which I'm going to explain later, and template engines like ERB, Hamon Slim. All of these non-JIT projects are supported by GitHub sponsors, so thank you for supporting me. And also, in the last 1 year, I've been almost as active as the Nobu, so-called patch monster. I made 999 commits in the last 1 year, and he has been doing 996. So maybe I'm now a JIT monster now. So for what's JIT? So first of all, we introduced the first ever JIT compiler, mJIT, in Ruby 2.6. And prior to that, I've been developing another JIT compiler, which is called LLRB. But Matt didn't like the idea of using dependencies like LLVM, so we ended up using a C compiler for writing a JIT compiler. And then we Shopify or Maxim, they invented or designed another JIT compiler called YJIT, which is a second JIT compiler introduced in the Ruby 3.1. And now this year, or yesterday, we released another JIT compiler called RJIT, which is a pure Ruby JIT compiler. So mJIT was written in C, YJIT was written in C first, and then written in Rust. And RJIT is purely written in Ruby, and that was released as a preview 1 yesterday. And RJIT replaced mJIT because mJIT has been optimizing some limited workloads like so-called opcarrot, which is an NS emulator, which is not really the production workload. So on the other hand, YJIT optimized Rails bench, or other web application workloads, and we wanted something that is useful for production. So mJIT is also using C compiler, which makes the implementation complex. So we wanted to remove mJIT for making the virtual machine simple. So the first purpose of RJIT was to remove mJIT to make the virtual machine simple. And RJIT kind of reuses the same infrastructure that YJIT uses to not complicate the implementation. And the second purpose of RJIT is to keep the ability to, or introduce the ability to have the third-party JIT capability. So the primary use case of RJIT is to make you write a JIT compiler, RubyJIT, custom JITs, and kind of make fun of it. So for me, I can experiment with some other ideas which are not necessarily compatible with the design of a YJIT, or you could also write a JIT compiler for fun, and that's the main goal of the RJIT project. The reason why we are working on JIT is this is a graph of the performance from the Ruby 3.5. So the blue graph is the interpreter, no JIT compiler. And then if you look at the graph, other graphs green graph kind of grow a lot in the Ruby 3.3, which is the mJIT and then replaced by RJIT. And the YJIT is the yellow bar. So if you compare the blue and the green and yellow, those yellow bars are much higher growth than the interpreter. So interpreter could be faster if you do some a lot of work, but YJIT or JIT compilers in general have more opportunities or the higher limits for optimizing the performance. So we kind of invest in a JIT compiler for making the performance much better because it's kind of a better way or easier way to make the significant progress. And if you listened to the yesterday's keynote, we are deploying the widget for storefront render in the Shopify's storefront application in production. And 3.2, we are running 3.2 for 99% of the cluster, and that's 10% faster on average. But now we are for the rest 1%, we are deploying the Ruby 3.3 Ruby master to those clusters, and that's 70 or 18% faster on average. So Ruby 3.2 is already slow for me. You should deploy Ruby master to make the best performance. So how many of you are already using YJIT? Please raise your hand if you are already deploying YJIT in production. Oh, thank you. So how to use YJIT. RJIT is just for experimental purposes. I'm not expecting you to deploy RJIT or MJIT in production. So to use the YJIT, you could use the so first of all, you have to build Ruby with the environment that has Rust installed, because YJIT is written in Rust. And if the environment has a Rust, Ruby build script detects the existence of Rust and automatically enables YJIT for you. And once you build or install the Ruby with YJIT enabled, you could enable that optionally by passing --JIT to Ruby command, or pass the variable called Ruby YJIT enable. So this brings us to the main part of this talk, Ruby JIT Hacking Guide. The idea of this talk is we used to have this great book, which is called Ruby Hacking Guide, and that goes over the details of the Ruby virtual machine and the internals. And that doesn't cover JIT compiler, because that's kind of an old book. So now, today, we introduce Ruby JIT Hacking Guide, which goes over the JIT compiler. And so basically, how Ruby JIT works is something like this. So if you have method like this, this just calculates the 3 and returns 3. Internally, Ruby interpreter compiles the Ruby code into the tree like this. And instead of working the tree, Ruby interpreter also internally compiles the tree into a sequence of some operations that are specific to the Ruby virtual machine. And as you listen to the Latin talk, this is a stack-based machine. So put object is a put instruction that pushes the object 1 onto the stack. So if you execute the first 2 instructions, you are going to have 1 and 2 in the stack. And when you reach the plus instruction, you calculate the plus addition 1 plus 2, and then pushes the 3 back to the stack. And then leave is basically the return instruction, which returns 3 from the method. And the way it works is, so in this talk, I'm going to kind of let you understand how to read assembly. So this is the start of that experience. So if you look at the, so this is the actual generated code of the YJIT. YJIT has the --YJIT -dump -disassemble option to let you see the actual machine code. And that also has the feature to dump the comments for assembly. And if you are not familiar with reading the assembly code, you can also just look at the comment, which actually I also do. Even if you cannot read the machine code, you can just look at the comment to understand what it does. So in this case, it has the put object 2, and opt plus. So the machine code for that is just doing those operations. And so let's go over this detail. And so as I explained, there's a dump disassemble option, which also exists for RJIT. And yeah, as I explained, you can just read the comment. I'm not now uncomfortable reading assembly with some comments. And so first instruction is the move instruction. So move is just an assignment. And you might be feeling it's kind of hard to understand assembly, but it's actually easy. Ruby has so many methods and syntaxes, but assembly language has only a few instructions, or not few instructions, but effectively, you only need to learn a few instructions for writing the RubyJIT, and because like most of the time you are going to interact with the 64-bit objects or like values, the combination of the things you need to use or learn is very limited. So move is the assignment, and the only thing or other things you need to do are just like add a sub, and if you know like move, add sub, and some like branch instruction and call and return, then you can start writing a RubyJIT. So which is why I kind of going over the instructions here. So as I explained, move is the like assignment instruction, and what it's currently doing is also now I'm kind of explaining the registers. So registers are like variables in Ruby. So you only need to learn two things. So first thing is instructions, and the other is registers. And registers are just a fixed set of variables. So you only have a very few set of registers, and you can use that for whatever purposes you want to use. So you cannot understand this instruction just because we are kind of deciding the use of the registers by ourselves. So in the YJIT, we use ESI or RSI for the stack operation purposes. So as I explained, Ruby virtual machine uses stack for operations for the Ruby instructions. And for example, when we see the first instruction, put object 1, we push the object 1 into the first slot of the stack, which is a stack 0, and we use ESI for stack 0, so which is why it's assigning 3 to ESI, and 3 is an integer representation for the 1. So object fixed number or integer 1 is shifted to left by 1 and plus 1, so it's 3, which is why it's move ESI 3. And similarly, we have move EDI 5, and EDI is the register for stack 1. So like we just assigning the 3 and 5, which is the object 1 and 2, to the stack first slot and second slot. And we also have another register, which is RAX. RAX we use in YJIT as a scratch register. So it's just a temporary register we could use internally in the YJIT code for whatever purposes. And here, in this case, we kind of use that for calculating the result of the addition of the integer 1 and 2. So RAX, finally, we have the addition of the 3. And this is a move, sub, add, and the reason why we are doing this is because integer is represented as the left shift and plus 1, and if you add those two things, you're going to get the result of the addition and left shift and plus 2. So you have to minus 1, make it 1 minus 1 to get the actual representation of the object 1 plus 2, meaning the integer object 3. And finally, we have the overflow check, because Ruby guards the overflow from you, and like if the integer is too big, it promotes the integer object internally from fixed num to big num. So it checks the overflow and then goes like jumps to another thing, which is the jump overflow, just JO instruction. So this is basically how the instructions work. And I want you to understand why we could write a JIT compiler in pure Ruby. So now I'm kind of explaining how I wrote the JIT compiler. So there's a website like this URL, which is authored by Hikarium. Ideally, you should be reading the official Intel Software Developers Manual, which goes over all the instructions in hundreds of pages in the PDF. But it's kind of hard to navigate the PDF. So I often use this website to search for the instructions and then jump to the index of the document. And it has the visualization of the bytes that are used for each instruction. So for example, in the first move ESI 3 instruction, this combination of the move instruction uses B8 plus some register index, and then after that, you have 4 bytes of the values that are going to be moved by that move instruction. So that way, you understand how the encoding works for each instruction, and then just convert that from the Ruby bytecode into the set array of bytes. And you could write Ruby code like this. So you just make an array object and then pushes the integers, like each element of the array represents a byte. And then once you have the array of bytes, you could use the array pack method to pack the array of bytes into the actual bytes in the memory. And then once you have the bytes, you can then write the byte array into a memory location by using a fido gem, which is a default gem. So by using the standard libraries, you can just write a kind of like JIT compiler. If you have function calls like mmap and mprotect to allocate that memory and then make it writable and then executable later, then that's all you need for writing a RubyJIT. So writing custom RubyJIT is easy. You can use in a Ruby 3.2, because MJIT was written in Ruby, you could also do the same thing, but I kind of recommend you to use RJIT because it has the capability of the --rjit disassembly capability if you use the method for doing that. So in that tutorial repository, I also use RJIT for that kind of purposes. And in the Ruby 3.3, you have the --rjit pause option to start the interpreter with the RJIT configuration enabled, but not starting to use the RJIT. And then you load the JIT compiler, you roll through it, and then you replace the method of the compile for Ruby virtual machine RJIT. And then once you do that, you can call the RJIT resume to start compiling those methods by your custom JIT. And building JIT is very much fun. So there are already at least a couple of people who are writing the JIT compiler in a custom Ruby code. So Aaron Patterson and John Houghton are both like Ruby and Rails committers, but like they're also writing a custom JIT on their own. So that kind of makes explains how that fun it is. And again, please try this repository to actually you try the actual RubyJIT development. And in the end of the repository, you're going to be able to compile the Fibonacci function. And if you look at this graph, the higher is better. And this is so this is a Ruby 3.3. The left is the no-JIT and RJIT and YJIT. So in the existing JIT compilers in CRuby, YJIT is the fastest. But if you go over this tutorial, you're going to actually write a JIT compiler that's faster than YJIT because you kind of ignore the actual compatibility problems. So it's kind of fun because you end up writing a JIT compiler faster than YJIT. And also, you could also think about how YJIT could be reaching this performance by going through this experience. So I want more people to be able to understand and discuss how we could make this kind of performance implementation possible in the future. So that brings us to the last section. So I already kind of went over the overview of how RubyJIT could be written, but now I'm going to kind of explain what kind of optimizations are possible if you start writing a RubyJIT. The first thing is side exit. Side exit is very important because side exit is so as I explained in the 1+2 example, you go to another kinds of code when the overflow happens. And in this example, both of the left and right code is actually the actual YJIT code, but the difference is the right side code is located in a very different place. And so if you could write those codes in a way that they are located in the different memory pages, and if you make that happen, then when you are using the left memory page, you will not be reading the code that's required for executing the right side code. What that means is when I think most of the time integer calculation doesn't really overflow, so you don't often need to use the right side code, which makes the reading the left side code more efficient. And so side exit is useful for making the code more compact. I think you heard that story that writing a JIT compiler could make the Rails bench slower in early experiments, but this kind of thing is very important for not making that happen. MJIT was also one of the JIT compilers that made Ruby slower in Rails, but the biggest reason was loading a lot of code in the same page or not making the memory layout small. So that side exit is very useful for that kind of stuff, for like making the code arrangement, memory layout you want to have. And this is also useful because when you start writing a JIT compiler, you could just start from a JIT code that just side exits to the interpreter. So side exit allows you to jump to anything, and like the anything could do something like just return the execution to the interpreter. If you do that, then you just write the perfect JIT compiler that's 100% compatible by just delegating everything to the interpreter. So for example, let's say you are only interested in integer calculation or arithmetic optimization, then you could write a JIT compiler that supports integer calculations, and then everything else will be the side exit to the interpreter. Then you have the JIT compiler that makes the integer calculation very faster, although but still making that compatible with the 100% with the interpreter. Next thing is method redefinition. So this is an example, again, from the this is actually, the hook is RJIT. So when you start writing a Ruby JIT, you may want to optimize the method definition. So in Ruby, because it's pretty dynamic, and whenever, so you could always redefine any method. So when redefinition happens, we have to kind of rewrite. So if we do something on the redefinition, we could do some optimization, like let the existing JIT code just jump directly to another like code that is responsible for running the callee method. Then if you do that kind of optimization, you have to throw away the code that directly jumps to the callee method when that callee method is redefined. So for doing that, in RJIT, we have a hook called on CME invalidate. And if we redefine that hook, you could redefine, or implement the invalidation for method redefinition. And that's also, by the way, how YJIT works. So like going like this into this talk kind of hopefully makes you understand how YJIT optimizes things as well. And same thing goes to like constants as well. When we have constants, it's not guaranteed to be actually constant in Ruby, because constants could be redefined by at any time. And if you have this kind of invalidation for constants, what allows you to do is you could just read a constant when the comparison happens and do the optimization over that constant, and then invalidate the code after the constant is actually redefined. So this is the couple of hooks that are needed for making that happen. And one of the things that I am currently working on in the YJIT is the register allocation for stack operations. So as I explained before, Ruby virtual machine uses stack for operating the YARB instructions. And as I explained, the stack 0 uses ESR or RSI, and the stack 1 uses RDI and EDI. And that way, we could just use registers as the stack operand instead of using the memory. So how Ruby virtual machine works is you use a set of memory to as a stack, but if you JIT compile that code, instead of using the memory as the stack slots, you could use registers as the stack slots. And in general, reading memory is slower than using register, so that makes the JIT code faster. And as I explained before, this is how it's assigned. And this is the Ruby 3.3 feature, which made some benchmarks significantly faster. So hopefully, once you upgrade Ruby 3.2 to 3.3, you're going to get optimization based on this. The thing that I currently haven't made yet is the register allocation for local variables. So similar to stack operands, local variables are also on the memory, and YJIT currently doesn't optimize that yet. So interpreter and YJIT have the same performance in terms of local variables. But the things that you need to care about when you are optimizing local variable is you have something like binding, and binding local variable get will allow you to read the local variable from memory. So you have to kind of de-optimize when the kind of method is called. So the things we are going to do is we kind of try to, so the other thing is a debug inspector API, which is another C function that allows you to do something like caller binding, or binding of callers. So because that kind of very risky of C API exists, you kind of have to assume that any C function call is going to make that kind of bad things. So the first architecture we are going to use is whenever we hit the C function call, we are going to spill the local variables from the registers into the memory. And this is actually what happens for the stack operands as well. So we can kind of reuse the same architecture. Another thing I want to explain is the polymorphic method cache. That's kind of touched by the next keynote as well. But so when you have something like array each on the left top side, that goes to the currently array each is implemented in C, but let's assume that it's actually written in Ruby. Then what happens is array each goes to the array each written in Ruby, and then that goes to the yield that calls a block of the given to the array each. And for the place that's calling the yield, it needs to support or handle multiple blocks for making that optimized. And we have, Ruby virtual machine has the mechanism called inline cache to cache the last code method, but it doesn't support polymorphic inline cache, which is the inline cache that supports multiple entries. So JIT supports multiple entries in a single call site. So for example, first of all, virtual machine doesn't support the cache of the yield, but JIT does. And in this yield call, it has the polymorphic inline cache to support both types of the blocks. At the same time, if you listen to the Benoit's talk yesterday, splitting is one other idea to make it further optimized. So if you use the polymorphic inline cache, what could happen is array each needs to support every single block that is executed with the array each in the program. So splitting is basically duplicating the implementation from some point. And so if you duplicate the array each and the block inside the code by the array each, then you could stop checking the multiple method entities entries in the place of the yield. And it also allows you to also do something like a method inlining. So if you inline those kind of stuff, the code could be something like the left side, and then you could do the optimization, which is not possible if that is not inlined. So yeah. That brings the conclusion. So what the takeaway is, I want you to enjoy the custom JIT development using the RJIT interface. And the goal of RJIT is not for making a competitor to a YJIT, but it's for learning from the experience by writing a custom JIT and making the ideas contributed back to the YJIT by making that doing that kind of experience. Thank you.